Hello everyone, ScienceBot is a podcast that shines a spotlight on the latest scientific technology from Japan. Your host is Ryan from ScienTalk. Have you heard of Parkinson's disease? It's a neurodegenerative disorder that affects millions of people worldwide. The main cause of this disease is the gradual loss of dopamine-producing neuron in a brain region called the midbrain substantia nigra. These cells have long projections called axons that form neural pathways to another area called the striatum. In Parkinson's disease, these crucial connections, known as the nigrostriatal pathway, damaged or lost. You can think of it like a major highway being cut off, preventing essential supplies, in this case dopamine, from reaching its destination. This shortage of dopamine leads to various motor function impairments, such as a tremor and slowness of movement. Currently, clinical trials are showing promising results by transplanting human stem cells derived of dopamine precursor cells into the brains of Parkinson's patients. However, there's a significant challenge. It's incredibly difficult to get the axons from these transplanted cells to grow long distances and reach their intended targets accurately within the complex environment of an adult brain. Imagine planting new tree saplings. It's hard to guide their roots and the branches precisely through a tangled underground and above ground maze to specific points. To overcome this major hurdle, this research team has developed an innovative new technique called nanopulling. This technology combined tiny magnetic particles, known as magnetic nanoparticles, with an external magnetic field to generate controlled forces within transplanted nerve cells. This essentially pulls the growing axon in the desired direction, much like a magnet guiding a piece of metal. In their experiment, the researchers first created an organotypic model that mimicked the early Parkinson's disease by culturing parts of the brain, including the midbrain substantia nigra and the striatum. Into this model, they transplanted human neural epithelial stem cells that had taken up magnetic nanoparticles into the substantia nigra region. When a magnetic field was applied to these nerve cells, the magnetic nanoparticles inside generated forces at the piconewton level. That's 1/trillionth of a newton, an incredibly tiny force. This force was able to guide the axons to extend in the direction of the magnetic field. The results of this technique were remarkable. Nanopulling led to new lights, which are axon-like projections, growing longer and in specific direction towards the striatum. Furthermore, the transplanted cells showed important signs of maturation and improved function, increased the branching of their processes, enhanced formation of the synaptic vesicles, and which are tiny sacs that carry neurotransmitters, and the stabilization of microtubules, which are parts of the cell's internal skeleton. This is like not just extending the road, but also building proper intersections and reinforcing the road structure itself. Importantly, these effects were also confirmed in human iPS cell-derived dopamine precursor cells, indicating the broad applicability and the potential for clinical use of this technology. The particularly significant aspect of this research is that magnetic nanoparticles and magnetic fields are already widely used in clinical imaging and therapy, such as in MRI machines. This means that the nanopulling technique could potentially be translated into a clinical application relatively smoothly. What's more, the study confirmed that applying these mechanical forces over a long period did not negatively impact cell viability or tissue safety. And this represents a major advancement in regenerative medicine for neurodegenerative diseases like Parkinson's diseases. If the magnetically guided axon growth can successfully reconstruct lost neural circuits, especially the neurostriatal pathway, it would dramatically enhance the effectiveness of cell transplantation therapy and help restore functional connection within the brain. Future research is expected to focus on optimizing the properties of the nanoparticles, evaluating long-term effects in vivo, and exploring its potential application to other central nervous system injuries and disease models. That's all for today's Science Spot, and this podcast is broadcast daily on weekday morning in both Japanese and English. I hope today's discovery has deepened your interest in brain science, even just a little. I'd love for you to listen to the podcast and post your notes and thoughts with the hashtag ScienceSpot. See you next time.